we're going to look at now, we're looking at section 2.6. And what's happening in 2.6 is we're talking about combinations of functions and domains. Now, combinations of functions are important because, well, the standard canonical functions, they might not explain everything we want to try to explain. For example, if we have some data and we plot that data, you know, sometimes data will come out into something kind of familiar, like half a parabola. But again, it might be something kind of different. So just like with piecewise functions, where we can adapt these canonical functions that fit our data better, same thing with taking combinations of functions. And so a lot of that's going to be looking at a certain kind of notation. In other words, when we are working with combinations of functions, well, how do we know? And there's a sort of a tip-off that you get, and that's the notation for these. So let's do some examples. Let's say f of x is x plus 3, and g of x is x squared. Now, in this case, if you want to add these together, we write it like this. That means we add f of x and g of x, like so. And what that will give us is x plus 3 plus x squared. Or we could simplify this and put it in standard form with the higher order term in front. And there we go, that's f plus g. Now for f minus g, we say this. And that gives us f minus g. And again, we'd probably put this in standard form. Minus x squared plus x plus 3. And so that would be f minus g. Now, there's also multiplication. And this means we take f of x and multiply it to g of x. So we get then we distribute this x squared, we'll get x cubed plus 3x squared. And there you go. Finally, division. For division, we write this. It's f of x over g of x. And we substitute for f of x and g of x, x plus 3 over x squared. That's it. There is actually one more. We'll talk about this. It's called composition. So that's your f divided by g. Now, composition's a little different. F, composition, that's what that means, g. Now, what this means is that we're going to take g and replace the x in the function f with g. So what you end up getting is this, f of g of x. So in the function f, wherever you see an x, replace it with g of x. So in this case, instead of x plus 3, we get g of x plus 3. And then we replace g of x with what g of x actually is. It's x squared. So we get x squared. So that's F composition G. And sure enough, you can do G composition F. So what that looks like is 2 G composition F. It'll look like this. G, where the x's in G, or the variables in G, well, in this case, the x, it's going to be replaced by f of x. So that means instead of having x squared, we have f of x squared, or x plus 3 squared. Keep the brackets here. If you're not familiar with brackets, they're the same as parentheses. They do the same thing. Usually what happens if you have inner parentheses, we use the arcs, the parentheses, and then outer parentheses, it's very common, use brackets instead. But they serve as the same thing. They act like parentheses. So that means we're squaring x plus 3. So it's the same thing as saying this. So we FOIL this and we'll get x squared plus 6x plus 9. And that's G composition F. So those are the major combinations that we're going to be looking at in this section. Now, something else this section discusses are domains. So domain, it's the set of all possible inputs. All possible inputs. So this thing possible, that's what we got to look at. Now with domain, it's the independent variable. It's where we get to choose goes into the function. And then based on how the function is constructed, what choice we've made, we get that output. The output depends on the choice we made and how the function is constructed. In this case, though, with domain, we're free to choose. But there are some inputs we're not allowed to choose. So we're going to look at some of those. First off, we can't choose the following. Anything that causes division by 0. You can't choose a number that's going to be a division by 0. So for example, if f of x is 1 over x minus 3, well, there's only one number that causes this denominator to be 0, and that's when x is 3, because 3 minus 3 gives you 0. And no other number that subtracts 3 will give you 0. Negative 3 subtract 3 is negative 6. So only when you have positive 3, 3 minus 3 gives you 0. So that means for the domain, we take all the numbers up to negative 3, but not including it. We hop over negative 3. And once we're beyond negative 3, just above it, we continue on. And so that becomes the domain for this function. If you were to graph this on a number line, three would have a hole, but you could take everything else. And so that's what we would have, no division by 0. So that's one thing we try to avoid. The other thing we try to avoid, since we're dealing with real functions, what that means is functions that work with real numbers and output real numbers. In other words, we don't deal with complex numbers. We want to avoid square roots or even roots of negative numbers. Note even roots of negative numbers, like negative numbers to the 1/2, that's a square root. Negative numbers to the 1/4, that's a fourth root. Those kinds of things we want to avoid. So for example, let's see if we have this. We want to make sure what's inside the square root is greater than or equal to 0. Now you can take the square roots of positive numbers, that's fine. You can take the square root of 0. Square root of 0 is 0. So we want to make sure this is greater than or equal to 0. And so to find the domain, we solve for x. And so what we find, x has to be greater than or equal to 4. So if this is greater than or equal to 0, x has to be greater than or equal to 4. So what that means, for a domain, here's 4, greater than is always to the right. So that means this side. And we can be equal to 4. That's okay. So we can put a closed dot on 4. Or if you're using the book, I think the book uses a slightly different way of expressing these. It uses brackets instead of dots. So I'd use a bracket here. And in the other example, what you would use instead of an open dot, you would use 2 parentheses. So for example, when x can't be equal to 3, instead of a hole, what you would put is this. And then you would continue. So parenthesis facing that way, parenthesis facing that way. That would be for the other example previous to this. But we're looking at this. So what this would be is a set. The interval would be 4. And that would be your domain. So the other things that can come up for domain, and we're not going to really deal with these, not for a little bit, but values, not allowed, or transcendent. Functions. So transcendent functions, these are things like tangent, the tangent of x. So in this case, x can't be multiples of pi over 2, whole number multiples. Well, you could do, yeah, you can't do whole number multiples of pi over 2. Hold on, give me a second there. You can do even multiples of pi over 2. That would be okay, because you can take the tangent of negative pi, for example. So let's say odd. So you can't do pi over 2, 3 pi over 2, 5 pi over 2. That won't work. Tangent of x will be undefined. Logarithm of x. X has to be greater than 0. We'll talk about this one later. So these kinds of functions, you have to be careful. There are just certain values that they cannot take. So just be aware of that fact. The other thing is, finally, values that are simply restricted. The best example of this I can think of, now these are just sort of done somewhat arbitrarily, or they're done based on the problem you're trying to solve. The classic example is time. Typically with time, it's greater than or equal to 0. Another example would be temperature in Kelvin. Say temperature X in Kelvin, X is greater than 0. Kelvin measures something, measures temperature based on what's called absolute 0. Absolute 0 is a somewhat theoretical temperature, if you will, that you can't ever get to. It's kind of like getting to the speed of light through velocity. You can get close as you can to it, but I gotta be careful, I'm not a physicist. I don't think you can actually reduce a temperature so low it's 0 Kelvin, though as I guess a target for temperature does exist. But again, better talk to a physicist about that. I don't think you can actually get to 0 Kelvin, but maybe I'm wrong. Better talk to a physicist. Anyway, there are certain restrictions based on the problem that are sort of traditional. We usually don't deal with negative time. And then this is considered a physical impossibility. Another restriction would be for velocity. Usually don't consider velocities that are greater than the speed of light because they're not physically possible according to current theory. Now it could be fun to play with some problems, like what if you could have less than 0 Kelvin? What would that possibly mean? What would happen if you could travel faster than the speed of light? There could be problems where you play with these ideas. But for the most part, if you're dealing with real world problems based on current theory, at least for the speed of light, we don't assume you can go faster or even equal to the speed of light. So there could be some restrictions that's just inherent in the problem. Anyway. So for example, let's take a look at this. So we can think about the 4 types of restrictions we're going to look for, or 4 types of things we want to avoid when we come up with a domain. We want to think about divisions by 0. Is there something here that could cause a division by 0? Are there square roots? Do we need to accommodate a square root? Are there transcendental functions? Or transcendent functions. Transcendental functions is what I should say. Transcendence, I think, is anyway, sorry, something else. Transcendental functions like tangent or log that we need to be careful of. There's certain values that they're going to be undefined for. And then finally, are there any restrictions? Like we want to make sure time is greater than 0, or our temperature is greater than 0, or we can't exceed the velocity of light. Well, we just have a function here. No restrictions are supplied. There aren't any transcendental functions, no logs, no tangents, no cotangents, things like that. And there aren't any square roots. But we do have a division where there's a variable in the denominator. And that can mean the possibility of division by 0. So for this one here, x plus 7 cannot equal 0. Subtract 7 from both sides, you get x cannot be negative 7. Now for this one, x minus 4 cannot be 0, which is the same as saying x cannot be 4. So we have two values that x can't be. It can't be negative 7, and it can't be 4. So let's take a look. So it can't be negative 7. That means we can take everything below negative 7, but we can't have negative 7 itself. Now, we can take everything between negative 7 and 4. That's fine. But we can't take negative 7 and we can't take 4. And then we can have everything above 4. That's fine. We just can't have 4. So what we get is negative infinity, negative 7, union, negative 7, 4, union, 4, infinity. And so that's going to be our domain. And that's it. Now let's take a look at another one. What if you have this? Now, again, we look for those things that could be restrictions. Are there square roots? No square roots. No transcendental functions. And, well, there's no artificial restrictions. But there is a division. So let's see. We need to make sure x squared plus 1 is not equal to 0. And this one's kind of a tricky one. Think about this one. The only way this is 0 is if you add something to 1, positive 1, that makes that 0. Now, the only thing you can add the positive 1 to make it 0 is negative 1. So can x squared ever be negative 1? Well, it can't. See, this is what happens if we try to solve this. If x squared is not equal to negative 1, take the square root of these, you get x is not equal to plus or minus I. So we better not use plus or minus I. Well, that's fine, because these are real valued functions. We're not going to be using complex or imaginary numbers, only real numbers. So we're going to avoid this no matter what. So it turns out on the real number line, we've got nothing to worry about. We can use any number on the real number line, and this will be fine. Now, if we were allowed to use numbers from the complex plane, where you have the real number line down here, but then you have the imaginary axis as well, and you have these two-dimensional numbers, we'd have to be careful of I on the imaginary axis, negative I on the imaginary axis. But on the real number line, we're totally fine. So all real numbers. Now, let's say we have something like this. Let's do this. Sorry. Now we've got a couple things. There aren't any transcendental functions. There are no artificial restrictions. We just have a function here. But we have a division and a square root. Let's take a look. Well, for the square root, I'll abbreviate square root, we need 3x plus 12 greater than or equal to 0. Or 3x greater than or equal to negative 12, or x greater than or equal to negative 4. So that's for the square root, so you don't end up taking the square root of a negative number. But now for the division. The square root of 3x plus 12 can't be equal to 0. Now there's probably an easier argument to make here, is that this will only be 0, this entire thing, if this is 0. So I mean, you could look at it that way. Because the square root of 0 is 0. So that means 3x plus 12 can't equal 0. 3x can't equal 12, negative 12. And then x can't equal negative 4. So we've got two restrictions here. We need x to be greater than or equal to negative 4. And in addition, x can't equal negative 4. So when we come up with a domain, we need to include all the restrictions. We can't just choose one or the other. We have to use both. So that means x has to be greater than or equal to negative 4 for the sake of the square root. In addition to that, we don't get to keep negative 4 after all, because if we do keep negative 4, yeah, the square root's going to be fine. If you let x equal negative 4, this becomes 0. You can take the square root of 0. That's fine. But then you'd be dividing by 0. So we have to bring all the restrictions together. So this is what we've got. So we have a restriction that says we need to be bigger than negative 4. But then we have another restriction that says, wait, you got to make this even tougher. You don't get to keep negative 4. So we have to keep both restrictions. And it's the restrictions that overrule. If one restriction says you can keep negative 4, and another restriction says you can't, the winner is the one that says you can't. You can't keep negative 4. So we end up getting this. Greater than or equal to negative 4, but then we got to cancel out that equal to with you don't get negative 4. And that becomes our answer. Moment. So one thing that comes up when you do these combinations of functions, you'll put functions together, you'll get a function in the end, and you'll come up with a domain. One thing to keep in mind, let's see here, is with compositions. So this is how this works. When you look at the domain for compositions, first off, what are going to be your restrictions? First, if x is not in the domain of G, So remember, this is f of g of x. So if x goes into g and it already blows things up, like we're already going to get division by 0 or square root of a negative number, well then if x is not working for g, it's not going to work for the whole thing. If x is not in the domain of g, then it's not in the domain of f composition g. So if this is messing up, it'll mess up everything else. So no go. The other one's a little subtle. If x is in the domain of g, but g of x it's not in the domain of f of x, of f, then x is not in the domain of f composition g. So if x is in the domain of g of x, that means it's perfectly fine. G of x is totally happy working with x. But if that g of x value, when you compute g, when you put that into f, it makes f blow up, then x is not in the domain. So let me do an example of that. So first off, what we get, if we take a look at the domain of g, number one, is there anything, any value of x that's not in the domain of g? We need to be careful. Well, g of x equals x plus 3 as a domain of, and then let's take a look at this. Are there any possibilities for division by 0? And no possibilities there. Nothing's being divided. Are there any square roots or even roots? No even roots. No square roots. Any transcendental functions like logarithm or tangent? Not seeing those. Finally, they just gave us the functions. There's no restrictions on x that are just there. So it looks like the domain is all real numbers. We can use any real number we want. So there we go. No restrictions on g. That's great. But is there a restriction that we're going to have to place on x because of what g might do to f of x? So here we go. F composition g of x is 1 over, oh, take that extra step there, f of g of x, which is 1 over g of x. Again, we're taking the x here and replacing it with g of x. Well, that's going to be g of x is x plus 3. Now here we do see a possible restriction. X can't be negative 3. So have a division here. Solve for x. X cannot be -3. So that means the domain for this composition, even though g of x can take any value of x, got to be careful. When g of x becomes 0, we'll get 1 over 0, and that's going to be a problem. So if g of x becomes 0, 1 over 0, we got division by 0. So what causes g of x to become 0? Well, when x is -3, it becomes 0. Got to avoid, can't have x not equal to -3. That's something we need to do. In fact, absolutely avoid it. So our domain, -infinity, -3, union -3. And that's going to be the domain for our composition. All right. So that's pretty much it. Let me pick a harder example. Let's say we have this. Looking for a good one. Now for this one, let's look at F composition G. So for this one, G of x, are there restrictions on G of x? Now again, we're taking F, we're inserting G of x. So G of x is 1 over x. So first off, is there anything that causes G of x to blow up? And there is. X cannot equal 0. So there we go. We have a restriction. Now, for f of x, f composition g of x means you're going to replace the x with g of x. Which is 2 over 1 over x plus 3. Or, I want to make sure 1 over x plus 3 is not equal to 0. Or 1 over x does not equal -3. And we can take the reciprocal of these. X is not equal to -1/3. So what we find out is we have 2 restrictions on x. There's the one we get from g of x, and then there's the one we get with f of g of x. So what we end up getting -1/3, 0. So we don't want to keep -1/3, but we can take everything below it. We don't want 0, we want everything above it. And we can take what's in between. So these 3 intervals, -infinity, negative 1/3, union, negative 1/3, 0, union, 0, infinity. And that's our domain for F composition G. If there's any questions, let me know. Other than that, have a wonderful day.